Wait, what?
But that doesn't say that?
What about you? You should buy your.
That's going to be saved on the YouTube channel forever.
In 2 years.
I'm going to hold you to that.
Well, welcome to Theory Lunch.
It's on camera. Yeah, everyone who visits the theory department.
Welcome to Theory Lunch. Today we have Yining Wang from the MLD department giving a talk. Yining is a second-year PhD student working with R.T. Singh, and his interests are in statistical learning theory and a bunch of other things, so you can talk with him afterwards. He's going to talk today about noise-adaptive, margin-based active learning and floor bounds. I almost remember that. Let's start.
Okay. Thanks, Nika. Okay, hi everyone. Today I will talk about basically two parts of my work. One is noise-adaptive, margin-based active learning. This is basically the upper bound part. So we have a learning algorithm which is noise tolerant to some of the parameters in the problem. And also the other bound would be a lower bound, which is kind of an improvement of an existing lower bound argument. So this makes the title particularly long. Okay, so I will first talk about the basic setting. So like in machine learning, the problem is we have data points. So for each data point, we have two parts. First part is xi. This is like the features or the observations. It is known for both the training and the testing process. And there is also a label yi. This can be either binary or a real value. For example, in image classification, the yi could be whether this image is a cat or a dog, or in regression, this yi could be the, for example, the predicted stock price in a market. So our goal is we have access to n data point. This is called training data. And our goal is based on the training data, we want to train a classifier, f hat, or learner, so that this f hat can accurately or approximately predict the label y based only on the observation of the data part x. So one example is the binary classification problem. In this case, the xi would be a d-dimensional real vector. This can be the feature vectors of your data, and the yi, the label, is usually binary. So positive would be the +1 would be positive examples, and -1 would be negative examples. So in the classical learning framework, we consider the passive learning scenario. In this case, the n training data points are assumed to be independently and identically distributed according to some underlying joint distribution D. And the goal of the passive learning problem is to train a classifier f hat so that the generalization error is minimized. So the generalization error is defined in terms of the probability of the learner making a mistake, and this probability is taken with respect to the underlying distribution D, which is not known to the learning algorithm. However, in more than data analysis, sometimes it is more interesting to consider an alternative framework, like this active learning framework. This framework is particularly relevant in applications when data points themselves are cheap, but labels are expensive. One typical example is, for example, medical data analysis. In this case, the data are not very hard to get because you have a lot of patients, you can do a lot of medical tests, but the labels are extremely hard to get because labels require domain knowledge. It involves like real doctors or medical experts to determine whether this patient has a particular disease or whether this test looks normal or abnormal. So in this case, the data parts, the X parts are cheap, but the Y's are very expensive to get. This motivates the entire active learning framework where the algorithm wants to minimize the label requests. So it wants to minimize the number of Y's it's seen, but it is allowed to more training data X. So more specifically, in this work, we mainly consider the pool-based active learning setting. So in this setting, the learner A has access to an unlabeled data stream. So this x1, x2, this unlabeled data stream are assumed to be IID drawn from some underlying data distribution D. And for each xi, the learner can make decisions. He can decide whether to query the label of this particular point xi, or he can reject this data point. So if a label request is made, the learner A will obtain a label yi, which is associated with this particular data point xi. And the goal of the algorithm is still to learn a classifier fpad, but this time the algorithm only wants to minimize the number of label requests, while at the same time, the algorithm can scan through a much larger but polynomial number of unlabeled data. And the sample complexity of this of the learning algorithm in this setting is defined in terms of the number of requests the algorithm made. So consider the simplest example where we want to learn a homogeneous linear classifier. In this case, the x is a d-dimensional real vector, and what we want to learn is a linear classifier W, and we assume that the true label yi is generated according to this simple noisy linear model. So basically, the sign of the inner product between the classifier W and the data point xi will tell you whether yi is more likely to be positive or negative. And we also have the noise term. So even if W transpose xi is positive, there is still some chance that yi, the label of yi can be flipped. It's just like the yi is more likely to be positive in this case. So in the past learning setting, the basic approach is to do this empirical risk minimization. So in this solution, we are given n data point yi and xi. In this approach, we want to find linear classifier W hat so that the empirical error, which is the number of mistakes made on the training data, is minimized. So although this problem is an NP-hard problem, but suppose you can solve it, then some existing theory shows that this W hat will be very close to W, and it will have small generalization error. So in the active learning setting, the problem is a little bit more uncomplicated, because this time you have to do two things at the same time. First, you need to decide what type of xi you accept, and second, you need to find a learning algorithm to find a classifier W hat using the labels you obtained. So yes.
So the sign is -1 or +1?
Yes.
And you're adding, what are you adding to that? The result is not going to be -1 or +1 anymore, is it?
Oh, it's like whether this sign agrees with the true label yi. So if it agrees, I make no error, but if it disagrees, I make one error, or I make one mistake.
It's an indicator for whether or not you made.
It's an indicator function.
I think maybe, are you talking about the plus noise or the indicator? Because the plus noise might be a little bit confusing.
Oh, the plus noise. I
The
see.
first equation on the screen.
I see. So yeah, this is kind of an inaccurate expression. So it's like the probability depends on the sign of the linear product.
Aren't you adding the noise to the inside of the sign?
Yeah, you can think.
You can think of it as like a noise oracle rather than
Yeah,
plus
yeah.
noise. That means that you look at the sign, but the sign is flipped with some probability of noise rather than. Okay.
So the sign is flipped with some probability.
Yeah.
So it also work to just put the noise inside the parentheses.
Well, that would depend on the magnitude of the.
Yeah. So if noise is inside and you have Gaussian noise, it's bounded error.
Yeah.
So it's like
So that's
constant.
the difference of those ones. I have a question for active learn. Is there a real difference between using a stream and then choosing one by one, as you receive the X, deciding whether or not you need the label, and this other active learning model that you get a pool of unlabeled data and then there's no stream, you look at all of the unlabeled data and then decide which ones to ask for labels?
I think these two are pretty equivalent because in the pool-based case, you can just requesting a sufficient number of unlabeled data points, and it will be very similar. But this is quite different from the selective case where you can actually select the x, because like this time, like in this setting, we requires a polynomial number of unlabeled data. So in that case, it might not be the case. Yes. Yes.
And are we assuming here that xi is drawn from distribution, or just that the noise is drawn from distribution?
Xi is IID. I'm assuming.
So yeah, xi is still drawn from distribution?
Yes, xi is still drawn from a distribution. And x and y will be drawn from a joint distribution in this case. Because this,
Yeah, exactly.
Yeah. Okay, so I will start with the very classical algorithm for this active learning setting, which is called margin-based active learning. It was proposed by Balkan, Border, and Brown in 2007. So this is actually a very, it's actually an iterative framework. So suppose the dimension of the data part is D, and suppose I have capital T number of queries that I'm allowed to make, and I will determine a number of iterations E. So this E will be determined by the algorithm, and it is typically a logarithm of the query budget T. So at each iteration K, I will do the following three things. First, I will determine two parameters. The B K minus 1 parameter, I will call it a margin parameter, and the beta K minus 1 parameter is kind of a search parameter. So the next step is I find small n samples. So small n would be capital T over capital E. So in this way, I have an equal number of samples per iteration. I will find this number of samples in a small margin. So this part means I will only keep those data points that are already close to the classifier WK minus 1 hat that I learned from last iteration. So this BK minus 1 will be the margin parameter. So imagine if BK minus 1 is infinity, you will keep all the samples. But as BK minus 1 shrinks, you will only keep those data points that are close to your last learned classifier. So this is the first step. This is kind of the data selection part. And then I will, after this data selection, I will request labels for all the capital T over capital E samples in this margin. And in this way, I will obtain n labels. And then I will perform a constrained empirical risk minimization procedure. So I'm still minimizing the number of mistakes I made on this data set. But this time, instead of considering all the classifiers, all the possible linear classifiers, I constrain that my learned classifier must also be close to the classifier I learned from last iteration. So it's kind of like I'm shrinking simultaneously the data points that I'm interested in, and I'm also shrinking the search space so that my linear classifier is constrained in this small ball. So the intuition of this algorithm is those points that are very close to your classifier are those points that have the most uncertainty. So instead of in order to improve the performance of your classifier, you have to constrain yourself to those data points that are most likely to be classified incorrectly. So the final output would be the learned classifier of the last iteration. So this is an algorithm proposed for the active learning setting. In order to analyze this algorithm, we impose some conditions on the noise distribution. So there are many kind of assumptions you can make on the noise distribution. For example, you can assume the noise is bounded, or you can even assume the noise has some certain parametric form of distributions. In this work, we consider the Tsybakov noise condition. So the Tsybakov noise condition basically says the excess error, which is the error of any classifier W minus the error of the optimal Bayes classifier W star. As the condition says, the excess error is lower bounded by a polynomial of the angle between W and W star. So intuitively, when W is very close to W star, my excess error should be very small. But the TNC condition asserts that the error cannot be smaller than a certain function of the angle between these two classifiers. So here, the alpha on the exponential of the angle is a key noise magnitude parameter in this TNC condition. So here I draw a figure of the excess error against the angle of the two classifiers. And we can see if alpha is small, the excess error will grow quite quickly. And when alpha is large, the excess error will first grow very, very slow when theta is very close to 0, but then it will grow even faster when theta is large. This is because when theta is close to 0, the large alpha implies a large polynomial, so the error will grow faster. So intuitively, when alpha is large, the problem is harder. It is because when alpha is large, when theta is very close to when your classifier W is very close to the optimal classifier W star, your excess error is very small. So it makes it harder to further make your classifier W close to the optimal classifier W star. So typically, large alpha would imply that your problem is harder. So in the main theorem of the margin-based, in the main theorem of Biochem, Broder, and Zhang 2007, they proved that by using the margin-based active learning algorithm they introduced, and by setting these parameters bk minus 1 and beta k minus 1 appropriately, they can prove that the excess error of the final length classifier W hat can be upper bounded by a polynomial of the term D over capital T. So here D is the dimension of the data point. So clearly, for higher dimensional problems, the problem is harder and your bound is looser. Capital D is the number of queries. So as we get more and more data points, the excess error is very small, and it goes to 0 when capital T approaches infinity. So this bound is better than any of the passive learning algorithm, because it can be shown that for passive learning, the best error bound one can derive is D over T to the 1 minus alpha over 2 alpha. So there is a polynomial improvement for active learning in this case. So I will briefly describe the proof outline, because in our presented noise tolerant analysis, we will closely follow this proof, and we will show in which part we revise the proof so that the algorithm becomes noise tolerant. So in the proof of the margin-based active learning algorithm, so this is a particular step at each iteration of the active learning algorithm. So I'm doing a constrained ERM, and I'm doing it over those data points that are within a narrow margin compared to the learned classifier at last iteration. So the key idea is to bound the excess error of this particular round using a decomposition of this excess error. So the key fact is that the excess error of the case round is upper bounded not only by the square root of D over T, which is known by VC type arguments, but also there is an extra factor of beta k minus 1 in front of this term. So as we decrease the search space beta k, and as we decrease the margin bk, we hope this we have the hope that this access error will be better and better when we continue with this algorithm.
I have a question.
Yes.
So how does the error depend on like the number of samples you're taking? I mean, so why did you decide to like? So I had like T budget.
Yes.
We decided to divide like T over E.
Yes.
Equally like in each of those steps.
Yes.
Why not different?
Oh, because capital E is so the number of iterations is assumed to be logarithmic. So capital E is assumed to be logarithmic. So any dependency over the T over E will be logarithmic. And here we have tilde O, so we ignore polylogarithmic factors in this bound. So we only care about the polynomial part. Because we want to prove, in this proof, we have the polynomial improvement. So naturally we ignore the polylogarithmic factors. Right. Yes, so the key idea to prove this per iteration bound is to decompose the access error into two terms. One term is the within error term. So here capital S1 is the area of the margin. So the first term shows that the within margin error is quite small because the access error part is square root of d over t by VC arguments, but the probability that any particular x lies in this margin is quite small. It is proportional to the margin parameter, and if we reduce the margin parameter, this probability can be very small. So this is why we have an extra beta k minus 1 term in front of the square root of d over t. And yes, and the next step is to bound the access error outside of this margin. So it can be shown that this bound is also proportional to beta k minus 1 because when x is far away from wk hat, the difference between the learned wk hat and the optimal classifier w star would be very small because it's outside of the margin. So you can imagine for these data points, both wk hat and w star are very confident of the labels. So there will be a small amount of error for data points outside of this margin. And combining these two terms of the access error, one can get the access error for each iteration of the margin-based active learning algorithm. So another thing to notice about this proof is that one should make sure the optimal classifier W star is always within reach. So this means W star should always be in the search space we considered. So in the language of theta, it means that the angle between W star and W hat k minus 1 should always be smaller than beta k minus 1. Otherwise, you would lose the Bayes optimal classifier W star. So this condition requires that you should be particularly careful about how you shrink the margin parameter bk and the search space beta k minus 1. Because if you shrink it too aggressively, maybe after certain iterations, W star would be outside of this search space, and you will not hope to get W star by using constraint in protocol risk minimization. On the other hand, if you shrink this margin parameter not that aggressively, then you cannot make this beta k minus 1 decay as fast as you want. So the bound would be loose. So you must make this search space beta k and this margin parameter bk decay in a very specific way so that it's not either too aggressive or too slow. So in particular, in the 2007 paper, it is shown that when beta k has a geometric decay and the decay rate is 2 to the alpha minus 1, when beta k has this type of decay, then I can guarantee that first of all the bound is not loose, and on the other hand, W star is always within the constrained ERM search space with high probability. However, one problem with this thing is you must know exactly what is the TNC parameter alpha in order to set appropriate shrinkage of beta k and bk. So, but in many practical applications, the alpha is not known. So it is generally not possible to know the magnitude of your noise. So when alpha is not known, it is hard to set key parameters bk and beta k of this algorithm using this particular decay. And on the other hand, a very strange thing is if the true parameter alpha of your noise distribution is not known, but the algorithm runs with the setting of some larger TNC parameter alpha prime. So like if I shrink this beta k using alpha prime instead of alpha, then this algorithm still works. But this time, the error bound will be in terms of alpha prime instead of alpha. So the error bound will, so the alpha here will be replaced by the alpha you actually put in your algorithm rather than the true alpha in your noise distribution. So this is a little bit disturbing because you really have to know the true value of alpha. And if you approximate alpha using something else, you will get an error convergence in terms of the approximate value. So this is not what is always want, because the difficulty of the problem doesn't change. It's only that you don't know the noise parameter. It's causing the error bound to be loose. So in our work, we slightly changed the margin-based active learning algorithm. The first, we slightly changed the algorithm to make it noise tolerant. So basically, for a wide range of alpha, you don't have to know alpha, and you don't even have to approximate it, and the error bound will automatically be in terms of this, this alpha of the unknown noise distribution. So the first step is we proposed an agnostic setting of the margin and search parameters. So like in this setting, capital E, the number of iterations is just 1/2 of the logarithm of the total budget, query budget capital T. And my setting of the search space, search parameter beta k and the margin parameter bk are completely agnostic. So I'm just shrinking beta k like 1/2 at, per iteration, and the margin is just like a linear function of beta k times some square root of the number of iterations divided by square root of the dimension. So to set these three key parameters, you no longer need to know the alpha of your TNC noise. However, this simple setting does not completely solve the problem, because as we remarked earlier, if beta k shrinks too aggressively, you cannot ensure that the optimal Bayes classifier W star is always within reach in your search space. So we need to change the analysis as well. So we observed that if you set beta k in this way, there would be a tipping point, which is an iteration k star in all of your capital E iterations. And this tipping point will depend crucially on the noise parameter alpha. And we show that the algorithm basically behaves in a two-phase manner. So in the first phase, which is before the tipping point, the algorithm just performs normally. We can ensure that the optimal classifier W star is within reach, and all the analysis would be the same. But for the second phase, we can no longer ensure that W star is within reach, because we shrink the search space and the margin parameter too aggressively. However, in this case, we can guarantee an excess error bound on WK plus 1 hat and WK hat. So it basically means I can no longer guarantee the excess error of my learned classifier is close to the Bayes classifier because it's out of reach, but I can still guarantee that the excess error is close to the error of my last learned classifier. So this basically means after this tipping point, my error does not propagate wildly. So I'm still in the final stage, my classifier is still quite as good has the arrow at the tipping point WK star. So you can add this inequality for all your iterations after the tipping point. It will show that the arrow of WE hat is very close to WK star hat, and on the other hand, so at the tipping point, my learned classifier will achieve the desired weight. So by combining these two phases, I can show that this agnostic setting of parameters work for all type of alpha. So the key fact here is that the tipping point depends on alpha, but the algorithm does not need to know the tipping point. So it's only used in the analysis. So in practice, you can just run this algorithm, and it is guaranteed that for any alpha, you have a tipping point K star, and the final result is as good as you want. Yes.
The last equation, is that just basically based on your search parameter? Because
yes,
just looking at a small number.
yes, because I'm looking at a very small number of classifiers. Otherwise, you can't guarantee WK plus hat is close to WK hat. Yes. Yeah, that is. Okay, so by combining this argument, we can show that this agnostic parameter settings will achieve essentially the same error rate, which is d over d to the 1 over 2 alpha for all alpha parameters. I'm sorry, this is typo, for all alpha parameters in 1/2 to 1. And this 1/2 is not crucial. This 1/2 can be replaced by any constant if you change this 2 here. So this 1/2 can be replaced by any constant, and I still have this arrow convergence for all the parameter alpha in this range. And this matches the upper bound in the not noise adaptive algorithm, like up to polylogarithmic factors. So this is the upper bound part of this work. So basically, the algorithm is noise adaptive, and we still achieve the same rate. And the analysis is like I have an extra phase with where the optimal classifier W star is out of reach. So the second part of this work is we show a matching lower bound that shows that basically this arrow cannot be improved whether or not it's noise adaptive or not. So in the lower bound question, we are interested in, is there any active learning algorithm that can do better than this d over t to the 1 over 2 alpha sample complexity on the TNC assumptions? So in general, the answer is no. The answer is no, and it's already proved. However, in that proof, the data distribution D is quite contrived, and in this work, we show that the d over t to the 1 over 2 alpha convergence is tight, even if the data distribution D is as simple as you can think about. So even if the data are uniformly distributed over the unit sphere, I can still show that the arrow convergence of D over T to the 1 over 2 alpha is the best you can get for any active learning algorithm. Actually, what we prove is even stronger. So we consider a stronger setting, which is called membership query synthesis or selective queries. So in this querying model, the algorithm A can pick any arbitrary data point xi, and the algorithm then receives the label y. So it no longer needs to have access to an unlabeled data stream. It can actually pick arbitrary data point in my data space, and it will get its labels. So it can be shown that this query synthesis model is more powerful than pool-based setting, which we considered before, where you have a pool of unlabeled data points when the data distribution D has density bounded away from below. So we prove lower bound for the Q-based setting, and this lower bound would immediately imply lower bound in the pool-based setting, when, particularly when the data distribution D is the simple uniform distribution. So, yes?
So the subscript P there, that means pool-based in the big O tilde notation on the previous slide? Right, big O tilde subscript P, does that mean?
Oh, what is no, this means with high probability.
Oh.
So because like this bound is
Yeah.
with high probability.
Yeah, sure. Yeah, exactly. Cool.
Last question. Okay, so our main tool is called Tsybakov's main theorem. That is a tool that is very useful in the proof of many information theoretical lower bounds. So in order to prove this lower bound, so basically it means for any estimator it cannot do better than certain parameter rho. I need to construct a set of models, or in our case it is a set of distributions. So I have capital M plus 1 distributions here, and the construction of my distribution must satisfy three conditions. The first condition is called separation. That means any two of my constructed negative adversarial distribution is well separated. So this means this means if, for example, if the true distribution is fj and I predict fk, then I have a big loss. So this is a separation condition. The second condition is closeness in the distribution. This condition asserts that the average KL divergence between any of the distribution in F0 compared to a particular distribution in F0 is very small. So here P of Fj is the data distribution induced by the Dray's distribution I constructed here. So this closeness condition means that though Fj and Fk are well separated in terms of the distance, I still cannot distinguish between Fj and Fk from empirical evidence because the KL divergence is so small that I need a lot of samples in order to distinguish between Fj and Fk from empirical evidence. And the third is a regularity condition, which says that basically all distributions should have the same support. And if I can construct these, if I can construct the adversarial examples that satisfy simultaneously these three conditions, I have the result that the best estimate f hat still cannot do very well. Like the distance is with high probability larger than rho, and the probability is guaranteed in this form. So all I need to do to get such a lower bound is I need to select a set of adversarial distributions that satisfy these three conditions at the same time, and I carefully control the parameters in this construction so that my lower bound actually matches my upper bound. So I will then talk about my negative example construction. So the first thing we want to ensure is separation. So for all pair of distinct distributions in my construction, they should be quite separated. So in our work, we want to ensure that I have a hypothesis class W. This class has M linear classifiers, and I want to ensure that the angle between any two pair, any pair of the linear classifiers is not small. So the angle is larger than or equal to t. This means any two hypotheses in this hypothesis class is well separated, and this can be done for any parameter t here using which is called constant weight coding. So basically, I can select an exponential number of linear classifiers so that any pair of them has angle bounded between t and a constant times t. This needs to be constant weight coding because I have the constraint that all the w should have norm 1. So like the positions, I can change the wi must be a constant, otherwise it will not normalize to 1. So yeah, so this is the first part of our construction, and it satisfies the separation. And second, for any two pairs of distributions, we want to construct the conditional distribution, the label distribution, so that the KL divergence. So the closest condition is satisfied. So this basically means for any classifier Wi star, I cannot distinguish it from W0 simply from empirical evidence. And also, it needs to satisfy the TNC condition for sure, because we operate onto the TNC assumption. So what we did is this. So in the upper figure, it is the label distribution for W0. In this case, the best classifier is the origin. So you can see it satisfies the TNC condition. So it is the label distribute. So the error rate is 1/2 when at 0, and it goes according to the theta to the alpha this decay. So in the lower figure, we consider an alternative, another hypothesis, which is Wi star. So here, the best classifier is Wi star. So for everything that is left from Wi star, the error should be smaller than 1/2. And for everything that is above Wi star, the error should be above 1/2. So this means Wi star is optimal. And also, my error distribution needs to satisfy the TNC condition. So what we did is actually very simple. So we again consider this range of a constant of t. So this t is sandwiches the distance between Wi star and the origin W0, which is in the top figure. So what we did is we slightly shift the distribution. We shift the distribution within this range slightly to the right, so that this distribution is a valid distribution for Wi star. But outside of this range, I immediately jumps. So I switch to the original distribution of the first figure. So you can see for any data point that is outside of this range, this distribution is exactly the same with the distribution of W0. It's only that within the small range, the small range of t, the distribution slightly shifts. And the shift is not very large because Wi star is very close to 0. So I claim that under this construction, the KL divergence between these two distributions are very close, so that any learning algorithm needs a large number of samples in order to distinguish between these two distributions. So this is the actual derivation for the KL divergence. So note that this derivation is slightly complicated because we have an active learning algorithm in mind, so that the data point xt, which is the tth data point the algorithm requires labels, the distribution of xt actually depends on all the labels the algorithm obtained in previous rounds. However, since my algorithm, since my algorithm is the same algorithm, so upon seeing the same sequence of data points and labels, it should have the same distribution for the next data point to request. So these two terms can cancel out each other, and eventually what I get is this term. However, when I expand this term, to capital T queries, what I get an extra conditional term here. So there's no way I can get rid of this conditional term because it's an active learning algorithm, and this x1 to xt can basically be anything. So instead of finding the distribution of this stuff, I simply take the supreme of all possible data points. So this explains the supreme here. And this supreme is what makes the active learning bound different from the passive learning bound. Because in the passive setting, this supreme is replaced by an integration. And that integration has a polynomial order term, is a polynomial term lower than this supreme term. So it is precisely this supreme term that makes the active learning simpler, more powerful compared to passive learning. So after derivations of this KL divergence, I can finally apply the Tsybakov's main theorem to get our lower bound. So I will choose small t. So small t would be the separation parameter. I will choose it to be at the order of d over t to the 1 minus alpha over 2 alpha. So this t decrease to 0 as I get more and more data points. And as I have said, by using constant weight codings, I can ensure that there are exponential, like e to the d or 2 to the d number of hypotheses in my hypothesis class F0. And by working out all the terms and throwing away constants, I can show that for any active learning algorithm W hat, the angle between W hat and the optimal classifier W star, the probability that it's lower bounded by this T over 2 is a constant. So that this means that no active learning algorithm W hat can do better than this T over 2 with high probability. And then we apply the TNC condition to translate this error bound in terms of angle to the error bound in terms of access error. I get this lower bound. So this means, suppose my data distribution has density bounded away from below, or my data distribution is uniform, and let the label distribution be all distributions that satisfy the TNC with parameter alpha. I can show that no active learning algorithm can do better. The access error bound can do better than this d over t to the 1 over 2 alpha. So this matches our upper bound up to polylogarithmic factors, and this lower bound is proved in for a more general data distribution class, for a narrower data distribution class. So D can be uniform, and actually this bound holds for the membership synthesis query model too. So it is a stronger lower bound than the lower bound in existing literature. So so these are the parts of work, like the main part of my talk. So in the remaining 10 minutes, I wish to briefly mention some possible extensions. So this is still ongoing work. So in this extension, we consider what is called proactive learning. So in this setting, we have m different users. So instead of one labeling oracle, I have m different oracles. And I assume these m oracles share the same classifier W star, but they have different TNC parameters alpha 1 to alpha m. So the quality of these oracles differ. Some oracles are better because they have a small TNC parameter, and some oracles are harder. And the TNC parameters, these parameters are assumed to be not known. At each iteration of the algorithm can pick a data point x. So this is the active part. And also the algorithm needs to select a particular user j, and then it will observe the label produced by that specific user on this data point. So it's kind of like I have active components on both my data selection and my label selection. And the goal is still to estimate the Bayes classifier W star, or to get a classifier W hat that has small access width. So the basic algorithm framework is still like, I can still perform margin-based active learning. I can do it in log T iterations, and at each iteration, I can use conventional bandit algorithms to address the exploitation trade-off. So I need to explore more users, but at the same time, I want to query the best user a lot of times in order to minimize my empirical error. Yes. So one key property that our noise-tolerant algorithm can be used for is that both the search space parameter beta k and the margin bk does not depend on the unknown TNC parameters. So I can just run this algorithm in log T iterations, and at each time I can just set beta k and bk in an agnostic way. I do not need to know what is the best parameter in this m users. I even do not need to know which user is the best. As long as I run this algorithm, I can automatically get my arrow bound that depends on the true parameter alpha here. So this is one extension we think our noise-tolerant algorithm could be used for in more applications. And this framework also has many interesting other extensions. For example, what if at each iteration multiple labelers can be involved? Like I can ask, for example, I can ask like both user 1 and user 2 to give me a label. Does that improve my error rate? And how does that improve my error rate? These are all very interesting extensions. Okay, that's all. Thank you.
Any questions? I was wondering, so when you don't know alpha in the previous, like in the more general case at the beginning, when you just have one user? Not in the proactive one.
Okay.
Just in the standard, not knowing the noise level, not knowing alpha parameters.
Yes.
What happens if you try a bunch of different alphas and then test for and kind of like test and approximately figure out how well you did at the end? Does that help you like make more acknowledged choices about?
You mean I don't know alpha, but I can test for?
Yeah, for example, you were saying if you choose an alpha that's bigger,
Yes.
your algorithm still works. If you choose an alpha that's too small, your algorithm wouldn't work. What happens if you try a bunch of them, like binary search for them, and then look at the outcome of the algorithm and see
I
if
see.
it's a good
The
alpha?
thing is, the strange thing is, the classifier would be good if you try a good alpha, but you don't know it. So you get a classifier which is good, you can't decide whether it is good or not. Deciding whether it is good or not requires a lot of samples.
I see.
So that's the
like
problem.
1 over epsilon rather
Yeah,
than logarithm.
that is also the problem here. So at iteration k star, you already get the best estimator, but you can't just say I stop because you don't know k star. So yeah, so I have a feeling that testing whether this access error is at this order is kind of at least not easier than actually getting one.
Yeah, you might have to test in the band, but it's not clear if that would be.
The band would
very good.
the confidence band will depend on this, and to get this, you need a lot of samples. So yeah.
Thank you. Are there other questions? Last time first.